didn't spell
Is this one different or not?
and I was like, how did this work?
Yeah, 'cause you know what? It's like
I'm really bad at spelling.
Okay, so we did exponential functions. Now we're going to do logarithmic functions.
Hold on. Hold up.
Sounds like a big plan.
No, that's
That's like a big plan.
we're just gonna shove
That's
that
a
underneath
big
the desk.
So when I'm talking about a logarithmic function, I'm talking about the function y equals log of some base a of x. The first relationship we are going to look at
Okay, hang on. So this is gonna be.
is a relationship that turns every log into an exponential. So exponential and log are linked that they can be rewritten as each other to solve for specific parts of it. So this logarithmic function is the same as the exponential function x equals a to the y. So the base of my logarithm is the base of my exponential function. What it's equal to is the exponent on my exponential function, and then what I'm taking the log of is my answer. So every single logarithmic function can be rewritten as an exponential, which means every exponential can be rewritten as a logarithmic. So that's what we're going to start with, is changing them between the forms. So the first one that we're going to start with is log base 5 of u, and I would like to turn this into an exponential function. Oh wait, this equals 2. That's helpful. The u is going to be,
like the equivalent to like the x up there.
Yeah. no, the u is the answer. She just said print it for her algebra class, so what is it again to say is it, then they might not have like a paper. There might just be online. Yeah, no problem. Okay, so the base of my logarithm is the base of my exponential. What my log is equal to is the exponent. And then what I'm taking the log of is my answer. So log base 5 of u equals 2 is the same as 5 squared equals u, which means that I can easily now solve for u, can't I? Because 5 squared is equal to what? 25. So by rewriting it in a different form, I'm able to solve for specific parts of this. How do we feel about that? We did this last year.
It'd be easier if I knew what log.
I don't remember us doing
So,
this at all.
no, we'll get into that.
I have no memory of this.
Oh, we
whatsoever.
did.
Oh, we did.
We didn't do a lot of it, but we did it.
So we
Okay.
did it.
I don't remember
Was
anything
it during,
like last year.
No, it was with our, no, it was in class. It was with log properties.
I don't remember.
Okay,
I know.
so the next one is log base b of 8 equals 3. I would like to rewrite this as an exponential function in hopes that it will help me solve for whatever my b value is. The base of my logarithm is the base of my exponential. What it's equal to is my exponent. And then what I'm taking the log of is what it's equal to. Okay, so this is the same as b cubed equals 8, which means I could solve for b on this one, correct? How would I get b? Cube root both sides.
Whoa.
So then b would equal whatever the cube root of 8 is, which is what? 2. So by rewriting it, I was able to solve for my variable b. Let's do another one. This let's say r equals log base p of q. I would like for you to rewrite this as an exponential. Alexa, what will be the exponential for this logarithmic function? P to the r equals q. I cannot solve this one clearly because I don't know what p, r, and q are, but at least I can rewrite it. Any major issues with that? Put your phone away. Any major issues with that or questions or concerns? Yeah. So let's do another one because they're not always as pretty as that one is. So now I have w equals log base 4 of 2t plus 3. And I would like to rewrite this as an exponential function. Jackie, what you thinking?
The 4 still be?
Mhm. What would be my exponent then? Nope. Whatever it's equal to is my exponent. So 4 to the w equals the 2t plus 3. Questions, concerns, or issues there? Okay, one more. Well, actually, two more, technically. So now let's go ahead and do log base 3 of x equals 5 plus 2z. I would like for you to rewrite that as an exponential. Jojo, what's it going to be? What's going to be the base of my exponential function? 3. What's going to be the exponent? Five plus 2z, which means my answer is what? Is what? X. So 3 to the 5 plus 2z power equals x. Questions, concerns, or issues? Okay. So now let's use this to solve a problem we would actually have because we've actually dealt with it. So let's say I have the function n equals 1,000 to the t. My goal here is to solve for t. Right? What would be the first thing I would do here? I would like to get t by itself. Right now, the 2 and the t are permanently attached. What's not permanently attached? The 1,000. How do I get rid of that? Divide it to the other side. So I have n over 1,000 equals 2 to the t. We've explored that every logarithm can be rewritten as an exponential, which means every exponential can be rewritten as a logarithm, and then that will bring my variable down to the same level, right? So the base of my exponential is the base of my logarithm. So this becomes log base 2 of what it's equal to, which is the n over 1,000, equals the exponent of my exponential. So n over 1,000 equals 2t can be rewritten as log base 2 of n over 1,000 equals t. If I knew what n was here, I could easily solve for my variable t now. And this is easier than doing the whole graphing thing that we did on yesterday's homework. So there are a couple more examples in here that we don't really necessarily need to look at. They're just more examples of using the conversion to solve for our variable. You're more than welcome to look at those on your own time. I do want to do one more, however, before we move on. So let's say I have log base 3 of negative 2 equals x. And I wanted to solve for x by rewriting this as an exponential function. Trent, how would I rewrite this as an exponential? Correct. So then I have to ask myself, okay, what exponent can I take 3 to make it equal negative 2? What do you guys think? Is there one? No, that would just flip it. It wouldn't make it negative. Is there any way to take a positive value and turn it into negative using exponents? No. So just because we can convert it
Yes.
doesn't mean we can't solve it. So this is a non-solvable function, or you could put no solution. So just because we can convert it doesn't mean it's always going to have an answer. Right? Super awesome.
I didn't say that.
Okay, so just like for exponential functions, there is a theorem about being one-to-one that we should write down that applies to logarithmic functions. I'm just going to put log because I get tired of writing logarithmic all the time. So this theorem is about log functions being one-to-one. And it has the exact same rules pretty much as the exponential did. So if I have two variable values that are not equal, then two logs of the same base with those values are also not equal. Taking the converse of that statement, if I have two logs with the same base that are equal with different variables, then those variables must be equal to each other. So this applies when we are solving logarithmic equations. So the example I would like to start with is log base 6 of 4x minus 5 equals log base 6 of 2x plus 1. So based off of these rules that we had, if I have two logarithms with the same base set equal to each other, then in theory, what I'm taking the log of should also be equal to each other. Knowing this allows me to just pull out that variable piece to set equal to each other and solve. So because they were both log base 6, I can essentially just get rid of that log base 6. And I'm solving only for what I'd be taking the log of. So then I have 4x minus 5 equals 2x plus 1. I want to solve for x just like normal, so I subtract this 2x over. I add that 5 over, and I get 2x equals 6. Divide each side by 2, and I get x equals 3. questions, concerns, or issues? That's pretty straightforward, and we did it a lot with the exponentials, so it shouldn't be that big of a change. We're gonna do one more equation one just as a practice, and we'll move on to graphing, because I know how much fun that is. So the last example I'd like to do for this one is log base 4 of 5 plus x equals 3. The 1-to-1 theorem rule does not apply here because I do not have two logs both with the same base, which means to solve this, I'm probably going to have to change it into an exponential function. So what would be the exponential equivalent to this logarithm? Marissa?
Huh?
How would I change that into an exponential function?
I only know the 4. Like,
The base, right?
and then the 3 would be
And that equals?
5.
I can actually solve this because I know what 4 cubed is, right? What's 4 times 4 times 4?
64.
So then this actually becomes 64 equals 5 plus x. Then to solve for x, I would just subtract the 5 over, and I'd get 59 equals x. And then I'd be done. So next we're going to graph a logarithmic function, Before we graph it, we need to know something about logarithms. So every generic logarithm is log base 10. So if we see something that is just log of x, we assume this is the same as log base 10 of x. For the most part, our calculators only deal with base 10 logarithms. So when I take a logarithm of a base that is not 10, I need to find a way to still be able to plug it into my calculator because it is near impossible to approximate a logarithm with a non-10 base using just paper and pencil. And it is possible, it just takes a really long time. So this is called the change of base formula. So change of base says, if I have a logarithm of base A taken to B, so log base A of B, and I wanted to plug this into my calculator, I technically need to change the base to base 10 in order to plug it in. To do that, I take log of B over log of A. And we would use the base 10 log that is in our calculator. So this is the change of base formula. If I wanted to solve this, I would do log of what I'm taking the log of divided by log of my base. And then that decimal would be the answer for this problem. This is how we graph logarithmic functions. This is the easiest way. So using this, I would like to graph y equals log base 3 of x. When we're graphing logarithmic functions, I'm never going to have a negative, and I'm never going to have it equal 0. So when I'm graphing this and plugging in x values, I'm going to start at 1. And then I'm going to plug in 2. And then I'm going to plug in 3. And then I'm going to skip forward a little while, and I'm going to plug in 9 just so I can see what's happening later on down the graph. Which means I'm taking each of these x values and I'm plugging them in for x and solving. So when I plug 1 in, this is the same as log base 3 of 1. This is not something I can plug into my calculator the way it is. So I have to do my change of base formula. So now this is the same as log of 1 over log of 3. And when I plug that into my calculator, I'm going to get a decimal. So everybody plug that into your calculator right now and tell me what decimal you get. We get 0, which makes sense because 3 to the 0 power equals 1. I do the same thing with 2. This becomes log base 3 of 2, which means when I solve it, I want log of 2 over log of 3. And I plug it into my calculator and solve. What do we get when I plug in 2? I like 4 decimal places because it's more exact. So 0.6309 or 0.631.
There's literally no difference in a graph.
Yes, but if you get in the habit of doing 4 decimal places, I don't have to make you change it in the future.
What?
Okay,
What are you talking about?
don't worry about it. So everybody get this. If you want to do 3 decimal places, that's fine. It's not going to change anything for the graph, as Gabe pointed out. But I do want you to get in the habit of taking 4 decimal places whenever you have a decimal. Okay?
Just did 2.
3. This becomes log base 3 of 3. When I solve this is the same as log of 3 over my log of my base 3, which is going to equal what? 1. Because 3 to the 1 equals 3. Also, the top and bottom are identical, so they cancel each other out. So I know what's happening close to 0. Let's try at 9 now to see what's happening a little bit farther away from 0. So this is the same as log base 3 of 9. When I plug it into my calculator using that change of base formula, I'm going to have log of 9 over log of 3. And that's going to equal what?
0.5.
2. Did you do it the opposite way?
Yeah, I did. Never mind.
Okay. Because 3 squared equals 9. So that's another way of thinking about it. Once I have these points, I can go ahead and graph it. You will graph no less than 4 points for a logarithmic function. No less than 4.
Well, that's harsh.
Right? Okay, so I go to graph it. I only need quadrant 1 for the most part because all of the x values I got were positive. My highest y value here was a 2, so I'm going to go up to 3 just to make it nice and pretty. And then I plot the points. So at 1, I guess I should scroll down a little bit farther. My y value was 0. So 1, 0 is the first point I'm going to put down. When I plugged in 2, my answer was 0.6309, which is a little over halfway to 1. When I plugged in 3, my answer was 1. Then I jumped all the way down to 9, and when I plugged that in, I got 2. Which means when I graph this, oh boy, that's terrible, but it works. It's going to look something like that.
What is log?
What is log? It is a base system for categorizing numbers. There's really no like fun, easy way of explaining what log is.
Let's not ask about it.
Anybody confused about graphing this? No, we're okay? All good? Okay. So now that we have converted logarithms into exponentials and exponentials into logarithms, and we've graphed logarithms, let's talk about the different types of logarithms that we can have. Because there are 2. There is the common logarithm, which is what we have been dealing with so far this lesson.
How much space in this gonna take?
This specific tiny little part takes 3 lines, but the rest of it takes a little bit. Which is log base 10, essentially. So if I have log of x, that is the same as log base 10 of x. And this applies when x is greater than 0, which is why on my graph, I didn't plot any negative x values and I didn't plot 0. Okay, because 0 would be an asymptote there. After the common log, what do you guys think the other type of logarithm is? The natural log. Uncommon.
The less favorite. The one we're probably focusing on.
The natural logarithm is ln. Hopefully you've seen that somewhere before. This is equivalent to our common log base e of x, and also only applies when x is larger than 0.
Also found in nature and it's brown.
That just made my day. Kill me. Kill me.
I'm too tired to comprehend.
Yeah. So then we're going to practice converting using these different types of logarithms so you can see the relationship. So doing an example like we had before, if I have log of x equals 2, what do I know about the base of this log? It's 10. If it doesn't tell you what it is, we assume it's 10. So then this is the same as log base 10 of x equals 2, which means I can rewrite this as an exponential function. Correct?
Yes.
My base would be 10, my exponent would be 2, and my answer would be x. And then I could solve for x if that's what I was asked to do. Anybody super confused there? Okay. So then, what if I have, I don't know, natural log of x equals 2. Natural log is the same as log with the base of what? E. So this is the same of log base e of x equals 2. Which means I can rewrite this as an exponential. And my exponent will be e squared equals x. Anybody super confused by any of that? Oh my goodness, we're almost out of time.
Yay!
Everyone felt it. Don't
The more
like
time
it
that
right
goes
now.
by, the closer to APS they were going. Oh,
Stop. Don't do this.
Oh my
The thing
goodness.
is,
Do you
the
see
closer
that?
to ABS is,
It's not
the
difficult, there's
closer
just a
we
lot
are
there
done.
and it's too early. I can't comprehend anything right now.
Okay, so there are a couple examples using this common log and natural log conversion to solve for x. I'm going to let you look at those on your own. I would like to jump to the inverses and then to the applications, or at least get one application problem in before the end. So because we have different types of logarithms that apply to different bases, we have inverses for these. By inverses, I mean that a natural log and an e cancel each other out, and a base log and a 10, cancel each other out. So that means log base 10 of 10 to the x is the same as just an x, because a base 10 and taking the log of 10 means that they cancel each other out because they're natural inverses. So whatever my exponent was on that 10 would be my answer. So whenever you have a log base 10 of 10, so the base and this value match, they're going to cancel.
So like it could be any number?
Technically, yes, but we usually only see it with base 10. This also applies if I'm taking a base 10 exponential to a log base 10 exponent. So a 10 base to a log 10 exponent cancels out, and my answer is whatever I was plugging into that log. So anytime you see a 10 and a log base 10, they cancel. The same thing applies for a natural log and a base e. So if I have a natural log of e to the x, natural log and e cancel each other out, leaving just the x that was in my exponent. This also applies if I have an exponential that I've raised to a natural log power. The e and the natural log cancel each other out, leaving just whatever I was taking the natural log of. So these are the 4 inverses that we are going to use to simplify and solve application problems. So these application problems are going to be extremely similar to all the ones that you've already done. I'm just showing you a different way of solving for these exponential values. So I would like to jump ahead, if you're looking at the notes, to application number 2, which is a Newton's law of cooling problem. I'm going to read the problem and then we're going to pull out the important information. Okay? So it says Newton's law of cooling states that the rate at which an object cools is directly proportional to the difference in temperature between the object and its surrounding medium. Newton's law can be used to show that under certain circumstances, the temperature T in Celsius of an object at time T in hours is given by the function T equals 75e to the negative 2t, where T is my temperature in Celsius and little t is my time in hours. I would like to manipulate this function and solve for little t. So another way of thinking about this is if I had an unknown in my exponent, this would be the way we get that exponent solved for. Okay, you had 2 problems yesterday on your homework that needed this to happen. What is the first thing that I would move from the right-hand side if I were trying to get little t by itself?
75.
The 75. So I would divide it out from both sides, which means on the left, I would have t over, capital T, sorry, over 75 equals e to the negative 2t, little t. Now I have a predicament. My little t is an exponent, which means I can't solve for it until it's down on the same level as the rest of my problem. So I need to cancel out this e right here to bring that exponent down. What is the natural inverse of e? Natural log. What I do to one side, I also have to do to the other. So I'm going to take the natural log of both sides here to cancel out the e, which means I now have natural log of t over 75 equals natural log and e cancel each other out on that right-hand side, and the exponent drops to be on the same level. So I have the natural log of big T over 75 equals negative 2 little t. What's the last thing I would do to get little t by itself? Divide by negative 2. So then I'm going to have natural log of capital T over 75 divided by negative 2 equals t. If you didn't like how fractional this one was, that is the same as negative 1/2 times the natural log of capital T over 75. And that's it. That's how you get the exponent by itself. How do we feel about that?
Wait, how do you know to use ln?
Because I had a base e, and the only way to get rid of it is to use its inverse, which is natural log. So if I had a base 10 there, putting a log on both sides would have canceled it out.
What if you don't have a base 10 and you cancel it out?
That's different. Most of the time, well, you could use a different, like if you had a numerical base, you could use a log of that same base. And it should
What if
work.
you have like an X?
That was rough.
If you had an x as a base and an x as an exponent, then you're in trouble. No, later down the road. That's a little too complex for this exact moment in time. Okay, we're gonna do another one, of course, because we have just enough time for that.
Dang it. Really have to use all of the whole new sheet of paper.
I'm so incredibly not sorry, but yes.
Now they have so much notebook left.
Okay, so just so you know, we're only gonna get one more done, and then there is another example that I would like you to look at for your homework, okay? Well, when I get your homework on Canvas. So this next example is example 3 in your notes. I will read it and we'll pull out the important information. So it says, assume a population is growing continuously. What does that mean I'm gonna use if a population is growing continuously? PERT. I'm definitely using PERT in here somewhere. Anybody who said E, you were right as well.
Yeah.
Let's say it's growing continuously at a rate of 4% per year. So my R value here is 0.04 because I changed it into a decimal. Approximate the amount of time it takes for the population to double its size. Okay, so this one's a little bit different because it didn't give me a population to start with. So if we assume that my population is P, what is my A going to be? 2P, twice whatever my initial population was. So now I have the equation 2P equals P E to the 0.04 T. So I replace the A with twice whatever my initial population was. I replace the R with the 4% written as a decimal, and T is what I'm solving for. So how am I going to get T by itself? What's my first step? Divide the P out. When I do that, I'm left with 2 equals E to the 0.04 T. We take the natural log of both sides. It's different than multiplying it, but I know what you mean.
Yeah.
So I'm going to take the natural log of the left, and I'm going to take the natural log of the right. The natural log and the E on the right cancel each other out, which leaves me with the natural log of 2 equals my exponent 0.04 T. And then what will I do? Divide by 0.04. So I'm going to have natural log of 2 divided by 0.04 equals whatever my time is. And then I could just plug that into a calculator because you have a natural log button on your calculator. And then that would give me my answer. Major questions, confusion, or issues with that? How many of you think this isn't so bad? A couple of you? Okay.
I know it's gonna get worse.
Not today. So there are a couple more examples that I encourage you to look at on your own time. If I get to them in my last hour class, I probably won't. But if I do, I will post that video as well. And your homework will hopefully be on Canvas at some point today. If not,
No homework.
no, I
We only
will
got the first
start a
half.
Google Classroom and put it on there.
Hilarious.
If I need 2 platforms, I need 2 platforms. Because we still got a whole lot of learning to do, and